this conference. It's really an honor, especially among so many familiar faces. I have to say, though, that being here in Grenoble for a conference without Jean-Pierre around, it feels just awfully wrong. So since passing, many things, lovely things, touching things have been written and said, including since the beginning of the week, and I'm not sure. I'm not sure it's my place. So I'll just get on and just talk about and this work, recent work with Mihai about these two topics, very classical topics in Kähler geometry, but finding canonical metrics. So here I'll be focusing on singular varieties and then applications to Chern classes inequalities for stable sheaves. So I will be giving somehow the first half of this talk, and Mihai will follow up in the next hour and a half to give the mostly focus on the maybe the more geometric application to the Bogomolov-Gieseker inequality. So yeah, I will be focusing on canonical metrics. So let me start with an introduction. As I was preparing this talk, I realized that I started a talk a couple of years ago in Grenoble exactly the same way with Yau's theorem. I guess it's a pretty common way to start a talk in complex geometry. So let me recall the celebrated theorem of Yau about the resolution of the Calabi conjecture. So there are several equivalent ways to phrase it. So one way to put it is, if you give yourself a compact Kähler manifold, another piece of data is you fix a smooth measure, so a smooth volume form if you want. And you normalize it. This is harmless in this way. And then the content of the theorem is that given such a measure, smooth measure, you can always find a Kähler form whose associated volume form is exactly that measure. Okay, so.
Just to be less ambiguous, I mean, a smooth measure can have zeros. Right? Just smooth.
I said a smooth volume form. To me, this is what a smooth measure is. Yeah. So there's also uniqueness, but this is not so important today. So there exists a unique, let me phrase it like this, a smooth function that is quasi PSH. And as I said, the volume form of the new metric that I'm going to call omega phi satisfies the Monge-Ampère equation. Okay, so you sort of fix a determinant pointwise and can find a Kähler metric globally that pointwise will have this. Okay. So somehow, if you have a better canonical measure or some measure that has geometric significance, then maybe you can use that measure to produce Kähler forms. This is essentially the content of Yau's theorem of Calabi conjecture. So how to produce measures? Well, smooth volume forms, they're in one-to-one correspondence with Hermitian metrics on the canonical bundle. There are many, many ways to see this. One way that I like to see it is the following. It's well suited for what will come next. So how to produce smooth volume forms. And again, this is a one-to-one correspondence, so I'm not claiming I'm getting anything special here. But this will be a little bit different later in the singular setting. So you pick H Hermitian metric on the canonical bundle. And once this, you can look at any local trivialization of Kx. Let's call it sigma, because sigma is a local holomorphic and form. And you form the expression, you wedge sigma with itself. Well, maybe I need to normalize. And you divide by the norm of sigma with respect to that said metric. Now this expression, you see if I replace sigma by any other trivialization, that amounts to changing sigma by non-zero holomorphic function. And by homogeneity of this expression, you get the same quantity, the same volume form, right? If you change sigma into another trivialization. So these quantities, they glue to a measure, a global measure mu that only depends on H. Okay? Again, there's a, you can reverse the construction. If you start from a smooth volume form, you can create a Hermitian metric on Kx. Anyway, now, if you want the Ricci curvature of this volume form is just the curvature up to the sign of H. Because sigma is holomorphic, so let me put it this way. If omega phi solves this equation, then with H, then the Ricci curvature of omega phi, which is minus I e to the power of the log of this determinant, is nothing but minus the curvature of Kx with respect to that fixed metric. Okay, which is another way to say that the first Chern class of X can be represented using any representative of that comes from the Ricci form associated to a Kähler metric in a fixed Kähler class. Okay, so a particular case of interest, and maybe that's the most celebrated case of Yau's theorem, is if Kx is trivial and H is the constant metric, or a constant metric, in particular it has zero curvature, and then the associated Ricci form of omega phi is 0. Okay, so if Kx is trivial or numerically trivial, you can always find Ricci flat Einstein and Kähler metrics. Okay, so this is the story somehow setting, and I want to explain what somehow survives for singular varieties, and what new questions come up. Okay. Okay, so roughly what happens when X is no longer a Kähler manifold, but maybe just a normal Kähler space? So maybe briefly, what is a normal complex space? I think everybody knows what it is. The notion of Kähler is sort of common, but maybe not so universally known. So to me, a Kähler metric on such a space, on a normal complex space of variety, is a Kähler metric on the regular part that somehow extends under local embeddings in Cn. Okay, so this is a very constrained condition, is a calorimetric omega on x for x. So if you want this is a global condition, you need to have a closed positive 1-1 form on most of the variety. And then you add a local condition that locally near any singular point, your form is dd bar exact and comes from a PSH function under some embedding in Cn. So one way to phrase this is such that given any local embedding in Cn, omega is actually the restriction of some calorimetric on Cn to x. So one other way to put it is omega extends to a caliform on Cn. So, and a Kähler space is a normal variety that can be endowed with calorimetric, to me. I guess I could have just... Okay, so now what about the rest of the business? So one assumption that is somehow crucial to make this whole process work and consistent is assume that Kx, so you can always define Kx as a reflexive sheaf, take the determinant of the Kähler differentials, but in general this will not be locally free. So if you assume that this is locally free, maybe up to taking a high power. So let's say it's a line bundle. Then you can reproduce the construction that I explained above, right? On a line bundle, even if it's singular, you can consider the notion of smooth immersion metrics in the same way. You will have local trivializations. That's basically the definition of what it means to be locally free of rank 1. And so you can still form this measure, at least on the regular part, and you can extend by 0 across the single locus. So given H, Hermitian metric, a smooth Hermitian metric, you can similarly construct a measure mu H on X. Again, you extend it trivially across a single locus. And it will have a density with respect to somehow the Lebesgue measure, which is not defined canonically, but let's say omega x to the n. So mu h will be some function positive times omega x to the n. Okay, so that comes out of the construction for free. Maybe an easy remark. It's an exercise. F is bounded. So here I don't assume compactness for x, so let's say locally bounded on x. That's equivalent to x being smooth already. Okay, so in other words, this measure, mu h, is always going to be singular, always going to have a density that explodes towards plus infinity as long as x has singular point. I can extend it. I mean, it doesn't quite matter. Yeah. It might have infinite mass. And that's your, yeah. But from now on, I will assume that it has finite mass. So good anticipation. Well, I haven't written anything. What is L1? Well, I haven't written the definition yet. Yeah. All I'm saying is it's never, F is not bounded. Okay, that doesn't matter which definition you take. This is one meaning. So mu of x is finite. Okay, or maybe locally. From now on, maybe x is compact. But this is just for convenience, right? This is really a local definition. I'll take this as a definition that acts under the setting where x has is Q-Gartenstein, that x has log terminal singularities. So obviously, there are other ways to see this, for example, using resolutions of singularities, but you don't really need this from the analytic point of view. You don't need resolution of singularities to define such singularities. Okay, so I'll assume this from now on. And so maybe to answer your question, so F will certainly be L1 in that setting, but it will be a little bit than L1. Okay. And for that, maybe you actually do need a resolution of singularities. Okay, so example, and that will sort of be central to this talk and Mihai's talk as well. An example of such singularities are quotient singularities, right? The easiest kind of singularities that one can make up. So what I call it quotient singularities. So locally Cn mod finite group are log terminal. And this is really easy to see because this canonical measure, mu h, when you pull it back to a local smooth uniformizing chart, it becomes a smooth measure. Okay, because essentially transforming the charts, I guess I assume G has no reflections, the local charts are quasi-étale. So when you pull back, so they're crepant, when you pull back a trivialization of kx downstairs to the local uniformizing chart, you do get trivialization of the canonical bundle Cn. Okay, so this tells you that the measure upstairs becomes a smooth form, and so in particular it has finite volume, and since you only took a finite cover, this property is preserved. Okay, so this is reassuring. And it turns out that log terminal singularities, well, in codimension 1, they're smooth because x is normal. But generically, if you look at the next bottom, this is the only type of singularities that appear. Okay, so somehow quotient singularities are the generic kind of singularity that a log terminal variety will have. Okay, so that's, if you want a theorem, I think it was written down. Greb, Quebecus, Kovac, and Peterman about a dozen years ago. That says that if x, so it was written in the algebraic setting, but the same proof sort of like goes through in the analytic setting. If x has log terminal singularities, there exists a proper set, really small, could I mention at least 3, such that outside of that very small subset, x is a orbifold. So x minus z has only quotient singularities. And it's actually much more precise, and this is important. As a byproduct of the proof, the singularities are not any quotient singularities. They're a product of Cn minus 2 times an ADE surface singularity. This is AD. Okay, and this will be born later.
I mean, your definition of terminal singularity is somehow strange. Because, I mean, you define it by global conditions.
So I said I defined it globally for the purpose of the talk, just out of convenience. But I could just say it's really local. Like this is all, like if you want, I can just say that mu has locally finite mass, or as the Radon measure. Yeah, but you're right. Yes, that's right.
I mean, it's not equivalent to quotient singularity.
In dimension 2.
On a surface, you still have multiple dimensions. With the surface,
Yes.
you have to allow non-AD singularities.
Okay, so maybe.
The S is just quotient surface singularity.
I guess this is probably what I meant. So quotient singularities. Yeah. Okay. All right. So let me now. Okay, in dimension 3. Okay, this is. What it means is there exists only finitely many points. Such that outside of this finite points, P1, Pk, X has quotient singularities. Okay. So now let me move on to the next board. Damn it. All right. So then the following analog of Yau's theorem holds. And this was proved by Institut and Zeriai. In 06. That says the following. Take so X omega X compact Kähler space with octerminal singularities. H Hermitian metric on Kx. Then you can solve the Monge-Ampère equation in the cohomology class of omega x with a slight twist. So you don't get smooth solutions. Okay, so then there exists a unique function phi. This is only bounded, but still has the positivity properties. With respect to omega x, such that so omega phi to the n is mu h. Okay, I also need to normalize as before, right? So and unique up to constant. So, of course, one slight difficulty is to define this object when phi is not smooth. but just bounded, and this was done by Bedford and Taylor in the 80s and can be generalized to singular settings. And one important outcome of the statement is that actually you get much better than this on the regular locus. Omega phi is an honest, a genuine calorimetric on X reg. Okay, so where this equation has to be taken in the regular sense. So this is a very important result. But what he leaves out of the story is, I guess you've got, if you want a smooth metric space, X reg and omega phi, but not much is known. Okay, one of the major outstanding issues or problem is to understand the geometry of omega phi near the single locus. Okay, so the asymptotics maybe of the behavior. Near the single locus. Okay, so maybe I can do a very brief and maybe partial state of the art. So the first general case that was settled and somehow for EGZ theorem actually is the effect has only quotient singularities globally. Then omega phi is compatible with that type of singularities in the sense that in any local uniformizing charts, it pulls back to a calorimetric. So this is what I call being an orbifold metric. Okay, so maybe let me write down if you have, so this guy that's smooth, this is a small neighborhood of a given point, and this is finite surjective. Okay, so the existence of such covers is guaranteed by the fact that X has quotient singularities. Then you can pull back this current omega phi, and it is a calorimetric. On V. Okay, so this already tells you that omega phi is not a calorimetric downstairs on X. Okay, so, but somehow this we knew already from an earlier remark. If you remember, I said that F, the density, does not have an infinity density when X is singular. We know that omega phi is not dominated, not even just by a calorimetric. So this is both good and bad news. It means that the solution that we get in the sense that I introduced over there, the solution omega phi that we get somehow is badly behaved. It does not induce a smooth calorimetric, but it's also good news in the sense that somehow it can read that there are singularities on the space, and its behavior should somehow be encoded, or the singularities of the space should be encoded in the behavior of omega phi. Okay, so this is a general philosophy, although we have very, very little evidence for this, except what I'm going to present.
First point is valid just on the locus when you have orbifold singularities.
What's that? Sorry.
Is the first point still valid?
So that's them. You keep anticipating my remarks. So if X is projective, then omega phi is an orbifold kilometric. On the orbifold locus. Get a set of points in X that have a neighborhood that is isomorphic to a quotient singularity. Again, this was proved. This appeared in a paper by Chili and Gangtian. I think the paper appeared in 19, but this is based on the construction of Chen-Yan. And it is somehow very complicated argument that relies on compactification, deep results that honestly don't really understand. Not my kind of math, compactification of stacks and things like this. So this is quite involved and has a lot of non-canonical arguments that appear in there that sort of prevent from generalizing it to the Kähler setting. I will say that in our paper with Mihai, we provide an alternative proof. That, in my sense, is much more natural. Doesn't use any heavy artillery, but is on the projectivity assumption. Essentially, all we use is the fact that, so the definition of quotient singularities is local analytically in nature, but for algebraic singularities, there's a theorem of Artin that tells you that much more is true, and it's actually local in the étale topology. So it's almost globally, it's almost a global notion in the Zariski sense, and this enables to somehow run the usual estimates. Okay, so if you're interested in that argument, you can have a look at our paper. The question is still open for Kähler varieties, so we still don't know. So I'm not sure if I want to say anything else before I... Yes, so that will be the object of the next theorem. Let me just say that there's actually a major result that's not, in a way, more impressive than all of the above, and that's due to Hein and Sun in 2017. That gives you one type of singularities plus some global assumption where we actually can answer the question, what does omega phi look like? And that's if, so X, we need X to be globally smoothable for technical reasons. And that is only has isolated A1 singularities, so cone over quadric. Okay, this is the sum of zi squared is 0 and Cn plus 1. If all your singular points look like this, and these are not quotients singularities as soon as n is 3, then omega phi is asymptotic in a very strong sense to a model metric very explicit on this affine cone called the Stenzel metric. That's Ritchie flat as well. Well, I guess in the case where you look at the Ritchie flat equation. Okay, this is a very long paper and relies on many, many tools, including many results about convergence of Riemannian spaces to singular spaces by Jaeger, Kolding, and so on. So this is by no means something that you can easily derive. So let me come back to trying to understand at least what happens in near simpler singularities, like quotient singularities that are not covered by this case, and that's the subject of the name theorem, of the next theorem. So same setting. So if X compact Kähler space, okay. Of dimension n, I guess. Okay. H Hermitian metric on Kx. Then there exists subset Z of Heike dimension, just like the set above. So proper analytic. Such that outside of Z, X has only quotient singularities. So this is not nothing new. But the point is that on that particular set, omega phi is an orbifold kilometric. Okay, so the upshot is, okay, maybe we don't know at this point the behavior of omega phi in any orbifold singularities, but any generic orbifold singularities in codimension 2, then it does hold. Log terminal, yes. Thank you. Okay, so two very brief remarks. So maybe one that I already sort of mentioned, but that will serve as a setting for the Mihai's talk, is that in dimension 3, this tells you that you can pick out finally many points out of that set. X is an orbifold and omega phi is an orbifold kilometric. Okay. And this kind of metric is actually useful for a bunch of geometric constructions, as we'll see soon in Mihai's talk. So in the remaining time, I'd like to go into the proof. And maybe highlight one crucial new ingredient that sort of saved the day. So there are 3 steps, and I'll mostly be talking about one. So step 1, before we do anything, so if you remember, I told you this metric omega phi, it's never, I guess I wrote it somewhere. It's never dominated by a kilometric, which means that you'll never be able to write omega phi is less than, I don't know, 1,000 times omega x. This will never hold near any singularity. However, you can hope for the other inequality. You can hope that omega phi has strict positivity and that it dominates a Kähler form. And this is a really thorny issue. It's not known in general. It's known in a bunch of particular cases, including in dimension 3, which would suffice for what we want to do anyway. But what I'm trying to highlight is that proving that omega phi is maybe more than a big constant, a small constant than omega x. This is not known in general. And so what we'll prove is something weaker, but that's enough for our purposes, is we'll prove that essentially it's true outside of that set Z. Okay, so for some epsilon, and this time epsilon is not a constant, that's small, but this is a continuous positive function. Maybe, let me put it this way. For some function on x, which is positive and continuous. No, actually, let me just put it like this. It's explicit. It's a continuous function on x, which is positive on x minus c. It's actually very explicit, the function. So, but yeah, okay. As long as you look at compact sets inside this open set x minus z, then omega phi dominates the calorimetric. It's more singular than this guy, but at least it has strict positivity. Okay. So in terms of potentials, it means that the potentials of omega phi that are locally defined are strictly BSH. Okay, and so I will not talk too much about this, but this is a semi-iterated use of Chern-Weil inequality, and it's a bit technical. I won't say much more about it, because I'd like to focus on the next step. But before I do so, let me point out a couple of consequences that are very much useful. Okay, when you do somehow metric geometry with singular objects, a lot of time what you want to do is say that the locus that bothers you, in my case the single locus, or maybe the locus z, you want to say that this is small. So of course z is small, like algebraically. We know it's a small set with respect somehow to the Euclidean volume form. But it somehow doesn't matter, because what we're interested in is the geometry of our Kähler, Einstein-like omega phi. And so what I would like to say is that z is, or the single locus of x is small, if you want, for some maybe Hausdorff measure that's takes into account omega. Okay, so that omega does not put a lot of size for that set. Okay, and this is what enables people to do analysis. You have to say single locus we don't know much is small, and then you can run the analysis as if that single locus did not exist. Okay, so maybe I'll just point out two consequences. So I'll draw a picture. So I fix a point x in x minus z. Okay, so I have a neighborhood of x where I only have quotient singularities, and maybe in order to have a little bit of room, so I pick a set u prime, and u prime is still compactly contained in x minus z. Okay, so you might still have some singularities, non-discrete singularities hanging around our neighborhood, right? And in geometric analysis, okay, you want to localize a bunch of arguments. So you need cutoff function. So you will need cutoff functions for the set u inside u prime. We'll need cutoff functions to take out the single locus. Okay, so there are two types of cutoff functions that are needed. So cutoff for u inside u prime, which means chi is 1 on u and supported on u prime. Okay, you can always embed x if you want and construct the standard cutoff. And maybe a row delta, a family of cutoff. For x thing, maybe in u prime. Okay, so there are two. There's this one set that we want to get rid of, and we want to localize the problem, so we need the function. And the outcome of this inequality, you still need to work a little bit, but since you work with quotient singularities, it can be achieved that you have I don't know if I should call it a proposition, but let me call it a proposition, that the gradient of chi with respect to omega phi plus its Laplacian is bounded. Okay, this is not quite obvious. Chi is a smooth function, but you take a gradient with respect to a metric that has some unknown singularities. At this point, you don't know that omega phi is orbifold. It's chi, yes, thank you. This does not come for free. And then the more tricky one is you want to get rid of the singular set and say that it is small. And by small, I want to say that it is morally dimension strictly less, codimension strictly more than 2, which is obvious, right? Because it has codimension at least 4 in the regular topology. But I want to express this in a metric sense with respect to our singular metric. And so one way to phrase it in geometric analysis is to say that we have cutoff functions that are highly integrable. Okay, and the power sort of reflects on the codimension of the set. And so what I'm saying is there exists epsilon positive such that the L 2 plus epsilon norm of this plus same thing for the Laplacian this goes to 0 when delta goes to 0. Okay, so you can always achieve L2. It's not very difficult. L2, having L2 to 0 means essentially your complex codimension 1. But we want to say better than this. And this comes to a cost. Okay, so why care about this? It's because of the next proposition. That will also appear in Mihai's talk. Proposition that says the following. So it's some type of Harnack estimate. You want to say that some function is bounded. You have a function, maybe that here on U prime, but that's defined away from the single locus. So you don't know exactly what it is on the single locus. And you just have integrability properties for it, and you want to deduce that is bounded. Okay, so this is a very classical setting in PDE theory. So if you have, let me put it this way, there exists a universal constant P, maybe depending on dimension and X, such that the following holds. For any non-negative function in, let's say, C2 of U prime reg. Okay, so this is C2. Okay, that's not how I want to phrase it. F positive F, so on U prime, F C2 is compact support. So by compact support, I mean that near the boundary of U prime it's 0, and F is C2 outside of the single locus. Okay, so we don't know its behavior near the single locus. And we want to show that it's bounded. Okay. And then two conditions guarantee that this happens. Well, first we need F to be highly enough integrable. So F is in LP of U prime. Okay, so P might be very large. Think of P very large but fixed. And we want a differential inequality of the form that the Laplacian of F has a one-sided bound. And the bound that matters is a lower bound, so it dominates some function g, which is also highly integrable. And under those conditions, f is bounded. Okay, so this is standard if u is Cn. What's that? Sure. Yeah. Thank you. Okay. So maybe it's not obvious why this kind of statement matters. And it might not be obvious why it's not that easy to prove. Damn it. This is terrible. Yes, so there exists P such that for any such function satisfying 1 and 2, then it's actually bounded. Connection with the term that I put on the board over there is that you want to apply this. So that's step 3. I'm jumping ahead. I'll go back to step 2 in a second, but use this. Did I erase that? So remember, in this setting, we have a uniform, and this guy is smooth, and this is finite. And the statement of the theorem, so the theorem is equivalent, more or less, to saying that for any holomorphic one form eta on V, maybe I don't know, that's V and V prime. I mean, not worry about compactness problems. Then the norm eta with respect to is bounded. Because in retrospect, P star of omega phi should be an orbifold metric, meaning that its pullback is a calometric on V. And so, of course, the norm of every holomorphic one form with respect to the smooth calometric is bounded, right? But if you have a current and you can show this property, and if your current satisfy a nice enough, I guess, PD, then this would be enough to show that omega phi is a smooth calometric once pulled back to the cover. Okay, so the point is I want to apply this proposition to F, which is eta. Okay, so there are two issues. First, it's not compactly supported. So I guess I need to cut it off. Okay, so that has compact support, the preimage of U prime. And then this has no reason to be LP for large P. Okay, so I will have to consider this some power gamma for a positive number gamma that will have to be very, very small, because we know somehow that F for gamma equals 1, we know that F is in L, in that case in L2. It sort of comes for free out of Chern-Weil inequality. So if you raise it to a really, really small power, then F will be highly integrable. And then you need to show that the Laplacian of F with respect to that metric, omega phi, is bounded from below by something that's also highly integrable, and that's sort of like Bachner formula type property. So this is the connection between why this proposition matters to our problem. So that's we'll end the proof, and let me come back to the proposition now. That ends the proof of the main theorem. Yes. So that's what I'm. So this function, it's some sort of it's Faulkner inequality that gives you for free, since you have a control on the Ricci curvature of the metric here, omega phi. There's a quick classical formula that describes what the Laplacian of this guy is. Essentially, G is F up to a twist. Yeah, minus F. Yeah. This is somehow like rather classical computation, which is why I'm not going to do it. OK, so in the very, very few minutes that I have left, let me tell you a few words about the proposition. And so this proposition, somehow the key new element, key input, is a recent series of papers by Guo, Fong, Jansong, and Jacob Sturm. Well, a couple of papers, mostly one that we use here, that of their paper, maybe plus epsilon, is that you can construct Green's functions on the regular part of any such compact Kähler space, and you have extremely good control on those functions. Okay, so there exists Green's functions, G, X, Y, or sometimes people think like this. It's a symmetrical expression. So this is a function on X reg squared with values, and you can have the value minus infinity. Maybe so I'll normalize them so that they're always non-positive. So smooth away from the diagonal. There are Green's functions. So it means that they're the fundamental solution of the Laplacian. Well, in the compact setting, you have to add a normalizing factor, but okay, so such that the Laplacian with respect to omega phi of gx is just delta x minus 1 over v, okay, in the distributional sense. Maybe I should say, yeah, so that's for any x and y in the regular locus. This is good, but if you don't know what happens near the singularities, this is completely unusable. And the key point is they're able to give quantitative estimates. So the suprema of gx on x reg is minus 1. You have bounds, so let me put it like this, of gx plus its gradient. This is finite and independent. So for all x. Okay, so that's a universal constant. There's a positive number and a universal constant c such that these functions that are defined on an open manifold x reg, they're actually a bit better than L1, and their gradient, again, is a bit better than L1. And certainly, this is very reminiscent to the kind of properties that show up upstairs. And this is, in a way, the bound is independent of the point that you choose, so it doesn't get worse as you approach the singularities. Okay, this is a key point. Okay, in 1 minute, if I may, why does this help us? And I will cheat, of course, as we always do. So in an ideal world, we want to show this, right? So we want to, f is non-negative, so I only need to show that f is bounded above. So I pick And I want to bound from above f of x. And by the identity here, f of x is just nothing but the integral. This is where I'm cheating. This is not true because f does not have compact support. This is the integral of Laplace of f times g. And there's a I want to see that this is bounded from above. So this is fine because f is in L1. And this is fine because g is non-positive, you remember. So this quantity, if I plug in the Laplacian inequality, this will be less than the integral over x reg of g times gx. OK, like this. And this is less than g and gx LQ. OK, and if p is large enough, then q can be taken close enough to 1. And we know that we have L1 plus epsilon bound. So this will be bounded above independently of x. OK, so of course that you can't do this inequality only holds weakly on the regular locus. So you have to cut out the singular locus and add cutoff function. And this creates a bunch of error terms. So you have to show that they go to 0. And this is not that obvious. So you have to use this particular cutoff function and their estimates and still work a little bit. But eventually, this is how the proof goes. So sorry for running a bit late. And thank you for your attention.